Greetings and welcome to a series of lectures on graphs and functions. This particular lecture focuses on lines. There's quite a few things that we're going to cover in this video. The first thing is to find the slope of a line. Generally, we'll be given 2 points, and then using those 2 points, we're going to calculate the slope of a line. Next is going to be looking at lines in particular forms. One will be point slope, another will be slope-intercept, and then the general form of the equation of a line. The next thing we want to look at is how do we distinguish between a vertical and horizontal line? What do they look like in terms of their equations? Another thing we're going to do is look at parallel and perpendicular lines to a particular line that we have in mind. If we have this line, how do we find a parallel line? How do we find a perpendicular line to the current line we have? And lastly, we're going to model data using linear regression. We're not going to get into all the steps of linear regression. We actually leave that into a statistics course, but it's important to see how linear regression looks like. It's important to recognize linear regression when you have a bunch of data and how you can use that line as a predictor. I've really said line a couple times, but in terms of mathematics, a line is an equation where you have 2 variables. We usually say x and y, but it could be any 2 variables. It could be t and r, but both of those variables are in the first degree. So there's no power on x that is like x squared or x cubed or y squared y cubed. Both of those are of first degree, and it's implied 1, so first degree. That's a linear equation. And when you graph it, it forms a line. Now, how we measure that line in terms of how steep it is will be called its slope. The rise, going this way, rise is the change in the y values, the y coordinates. And the run is the corresponding change in the x coordinates. So rise, run. And slope is really just those 2 things, the change in y over the change in x, rise over run. You may have heard it called that, rise over run, which is your slope. Now, positive and negative slopes depend on where the change is happening. A positive run indicates a change to the right, a positive change. So when you go to the right, it increases in height with your line. In essence, you run over and then you have to go up to catch up with the line. Versus a negative run means that when you run over, you have to go down to catch the line, and that's a negative rise. Now, here's the thing. We talked about positive change in our rise. We've talked about negative change in our rise. But we do need to consider, what if there's no change? When we have no change in our rise, we stay on the same line horizontally. And that means our rise is a 0 run. There was absolutely no change in our rise. When our run is 0, that means there's no change in our rise. And the problem with that is that it forms a wall and there's no slope, right? To a straight up and down line, there is no slope. Mathematically, it's undefined. How we do this is when we have a horizontal line, that is 0 slope. And as your slope grows and we are positive, our positive value gets greater and greater and greater. Likewise, when we're at 0 and we're negative, we get more and more and more negative until we're fully vertical. And therefore, there is no slope. We also say the slope is undefined. Now, of course, there's got to be some math involved, right? So let's say we have 2 points, and we'll just call them P and Q. Our slope is going to be rise over run, and the rise is the change in the y values, and the run is the change in the x values. Another symbol for change is delta. It's the Greek letter delta. So delta y over delta x, the change in y over the change in x. Generally, you will be told it's y2 minus y1 all over x2 minus x1. But it honestly doesn't matter. It could be y1 minus y2 as long as your denominator is also in that order, x1 minus x2. It won't matter mathematically as long as you line up your values, so y2 over x2 and y1 over x1, then you'll be in good shape. If our x values are exactly the same, meaning we have a vertical line, that means x2 minus x1 is 0. And you know, when we have a fraction with the denominator of 0, it is undefined. So a slope technically of a vertical line has a 0 denominator, and that is undefined. Let's sketch the graph of the line that passes through a couple of points, and we're going to say our first point, P, is 1, negative 1, and our second point, Q, is 3, 3. We're going to find and interpret the slope of the line. So mathematically, we're going to find the slope, and then we're going to interpret what those values mean for the slope of the line. Let's graph our line between P and Q. When we run over 2, we're going to rise 4 to get over to the next line. Okay, so we can create a little right triangle between the points. So technically, mathematically, we've already done our formula. We decided we had to go over 2 to the right to get to this 3 in Q, and then we had to go up 4 from negative 1 to 3 to find the line again. This is our slope, rise over run. Rise is 4, run is 2. So 4 over 2, but of course it's a fraction, so we can reduce that a little bit to 2 over 1, aka just 2. The slope here is 2. Now mathematically, let's go ahead and calculate that through. We're going to say the rise over run, the change in the y coordinates over the change in the x coordinates. And let's plug in all of those values. Q is our second point, so we're going to list that first, then the coordinate of the p values. 3 minus negative 1 all over 3 minus 1. 3 minus negative 1 is 4, and 3 minus 1 is 2. 4 over 2 is 2. So mathematically, our slope comes out the same as if we calculated the rise and the run and put it into our rise and run. Both of it works. So how do we interpret the slope? In essence, it's for every 2 units of change in y, there will be 1 unit of change in x. Now, because both of these are positive, when we change in the positive direction, it will be 2 units for y, 1 unit for x. If we can also put negative signs in front of both of them. So for every 2 units negative direction for y, there will be 1 unit negative direction for x. That's what the slope means. All right, let's talk about the slopes of lines. The first thing is scanning the graph from left to right, lines with a positive slope will rise and lines with a negative slope will fall. Now, I was just told that for left-handed people, this seems a little backwards, and I was a bit surprised about that, but I guess because we're so used as right-handed people, we see things from left to right just fine and our hand doesn't get in the way. But when you're a lefty, you're really kind of looking at everything from the right of your hand. So this might feel a little backwards to you. Like I said, a student just told me, well, I'm a lefty and this seems backwards to me. But if you're looking at the graph from left to right, just as the way that we read, lines with a positive slope will go uphill. Lines with a negative slope will go downhill. The greater the absolute value of the slope, the steeper this line is. Okay, the larger the number, the more steep the line is when you take the absolute value. A 2 might look like this. A negative 2 might look like this. It's pretty steep, right? Both of those are pretty steep. Versus a half will look like this. Negative 1/2, positive 1/2. It's not as steep. The closer you get to 0, there will be no slope whatsoever. Well, there'll be 0 slope at 0. You'll be on a flat plane at 0. But the larger the absolute value is, the steeper it is, either negative or positive. Slope of a vertical line is undefined. We've already explained that. It's because your denominator becomes 0 and therefore it's undefined. The slope of a horizontal line is 0. When we are given information about the slope and a point, we can use the point-slope form to find the equation of a line. Now, this doesn't automatically give us the equation of a line. It's in the form of the equation of the line. So given a point and the slope, we can find the point-slope form of the equation of the line. Now, the first y, it's y minus y1. This first y is a generic y. It's the one where if you're given a value of y, you could plug it in and then you could find the x. It's just a generic y versus this y1 comes from the point x1, y1. So y minus y1 equals m, the slope, times the quantity x minus x1. Again, this x1 came from the point. This x is a generic x. So let's look at it as an example. Let's find the point-slope form of the equation given a point and given the slope. And then we're going to solve for y, meaning we will get into the form, well, y is on one side and everything else is on the other side. So y will probably be on the left. All the rest of the values will be on the right. Okay, here is our point-slope formula. Y minus y1 equals m times x minus x1. Plugging in 1 for y1, plugging in negative 2 for y1, 1 for x1, and 3 for slope, we end up, and simplify slightly, we get y plus 2 equals 3x minus 3. Now I got to get it saying solve for y, so I want to move that 2 over. So subtract 2 from both sides, we get y equals 3x minus 5. Okay, given a point, given a slope, we get down to the equation of a line. Let's find the equation of a line when we're given 2 points. Now we have the point-slope formula at our disposal, but the problem is we're given 2 points. We weren't given the slope. So the first step would be, okay, using these 2 points, let's calculate the slope. And then once we've calculated the slope, we can use one of the points we were given to find the equation of the line. So our first step, use the 2 points to calculate the slope. So our slope is the change in y over the change in x. So y2 minus y1, x2 over x2 minus x1. So 7 minus 1 over 3 minus negative 2. That gives us 6/5. Now that we have the slope, we've calculated the slope, we're going to take the slope and one of the points. It doesn't matter which point you use. I'm going to go ahead and use 3.7 and our slope of 6/5. Using our point slope formula, y minus y1 equals m times x minus x1, we're going to go ahead and plug in everything we know. Our slope is 6/5, our x1 is 3, our y1 is 7. Now we're going to distribute, we're going to add 7 to each side, and we ultimately get y equals 6/5 x plus 17/5. And that's the equation of our line when we're given 2 points. Always, when you're given 2 points, it's a 2-step problem. Find the slope, then use the slope in one of the points to use the point-slope formula to find the equation of a line. Let's look at another example. We're going to find the equation of a line given the slope and the y-intercept. So first we're going to find the point-slope form of the equation, and using the slope and the y-intercept, then we're going to solve for y. Our line passes through 0, b, where b is our value on our y-intercept where our line crosses. It's just a generic location. I don't know if it's negative, I don't know if it's positive, it's just b. Now using our point slope, we are going to throw in 0 for x1, b for y1, and our slope is just a generic slope. The point of this exercise is you can get to the slope-intercept form by utilizing what you know about the point-slope form. Okay. Y equals mx plus b is slope-intercept form of a line. Now, let's graph using a slope and an intercept. The good news is it is blatantly out there. There's not a lot that we have to do to be able to graph this equation. We have the intercept. Where does it cross on the y-axis? And using that point, we can use our slope, rise over run, to find another point. Once we get those 2 points, connect the dots, we've got a line. Now, here's our y-intercept. Using our slope, we run over to the right 3, up to plot our next point, connect the dots, we have our line. It's really kind of straightforward. When we're given this intercept and given the slope, we can use those 2 facts. Now, if my slope was just 4, then what I would do is write that as a fraction, 4 over 1. I run over 1 up 4. If I had a -2, well, that's -2 over 1. I run over to the right, and then down 2, because it's negative. I can still use a whole number in terms of rising and running, as long as I can still use a whole number if I want to rewrite it as a fraction, that whole number over 1, and utilize the rising and the running. Horizontal and vertical lines are very special lines. The equation of a horizontal line through some point, and I'm just going to say our generic point is h, k. Our line equation is going to be y equals k. For a horizontal line, the y value does not change. X can change all it wants. That could be h, that could be 1, that could be 0, that could be 1/2, that could be a -3/4. K will not change. And therefore our equation is y equals k. For a vertical line, it's where our x value doesn't change. Our x value equals h. And therefore y could be anything it wants. Y could be 0, y could be 1, y could be that -3/4. X does not change. Let's look at these equations and figure out what's going on here. So looking at A, y equals 2. That means y is never changing, and it really doesn't matter what x value you put in there. Y never changes. Therefore, this is a horizontal. It never goes up and down any more than what it is. That means it's a horizontal line. For B, the x never changes. That means it doesn't go right or left any from where it starts. And therefore, it's a vertical line. No changing left and right, and therefore it's a vertical line. Now, you could rewrite this as 0 times x and then plug in some value for x. Let's say 2. So now our point is 2, 2. Plot it. Let's try x is now 3. So your point is 3, 2. So it doesn't matter what x is. It could be anything. That line never changes. It's always horizontal. And our slope is 0. Don't forget, a horizontal line has the slope of 0. For a vertical line, X is 4 everywhere. Everywhere, and y is completely arbitrary. You can pick any y you want. Again, you could rewrite it as x plus 0y equals 4, and then choose a y value, and then that way you could get a second point. Just remember, a vertical line has an undefined slope because the change in x is 0, and that's in your denominator. Now we talked about point slope, we talked about slope-intercept. Now let's talk about the general form. That's where you have ax plus by plus c equals 0. Yes, equals 0. A, b, and c are constants. A and b are not 0. Can c be 0? Absolutely. Absolutely. If the b is 0, then you only have an x and you don't, I don't want to say you don't have a line because then you have a vertical line. And if a is 0, you have a horizontal line. Okay. But you don't want both of them to be 0 at the same time, because then if they are, then you just have a constant left over, and that's not good. So for it to be a line, a can be 0, but b cannot be 0 at the same time. And likewise, if b is 0, then a cannot be 0 at the same time. So let's graph. Find the slope, find the y-intercept, find the x-intercept of this general equation of a line. 3x minus 4y plus 12 equals 0. And then we're going to sketch it. The first thing we want to do is, for me, the easiest way to get the answer for the slope and the y-intercept is to solve this for y. Solve the general equation for y, and you will have immediately the slope and the y-intercept. You still need to find the x-intercept, but once you get it into this slope-intercept form, you immediately get the slope and you immediately get the y-intercept. So we can answer that immediately. Slope is 3/4, y-intercept is 3. Now if I want to find the x-intercept, I have to make y 0 and solve for x. Okay. So the x-intercept is -4. And let's go ahead and sketch it out. Okay. Using my 2 points, my x-intercept is -4, 0. My y-intercept is 0, 3. And connect the dots. Connect the points. Okay, so let's infer the height from a bone of a femur bone. So you're given this formula. The height of a human male is related to the length of his femur by this equation. H equals 2.6x plus 65, and all of these measurements are in centimeters. So it turns out we figured out the femur bone is measured between 45 and 46 centimeters of the height of Wild Bill Longley. And we want to know, well, if his femur bone is 45 to 46 centimeters, how tall was he in real life? So what are we going to do? We're going to plug in these values and see what his height could be. So let's first take 45 and then we'll take 46 and plug them each in separately and figure out what his height range could be. Given 45, we see his height is 182. So it's 2.6 times 45 plus 65 ends up to be 182. 2.6 times 46 plus 65 is 184.6. So we know if his femur was somewhere between 45 and 46 centimeters, his height, using this calculation, would be between 182 and 184.6. Now let's calculate that into inches and then feet. So we know in inches it's 71.7 and 72.7. Now 6 feet, 5 feet is 60 inches, 6 feet is 72 inches, so he's about 6 feet tall, about 6 feet. Let's talk about parallel and perpendicular lines. Given two lines, we'll just call them L1 and L2. If they are distinct lines, meaning they're not sitting on top of one another, they are distinct lines and they have their own slopes, then if they are parallel lines, their slopes will equal one another. For example, if line 1 slope, if this slope is 2 and we have a parallel line, then the parallel line slope must equal 2 as well. Likewise, if this slope is -1/2, then a parallel line, see if I can get, there we go. Parallel line would be also have the slope of -1/2. For lines to be perpendicular is if you multiply the two slopes together, they equal -1. In other words, the slopes for perpendicular lines are opposite reciprocals of one another. Opposite reciprocals. So remember that line of 2? If it is perpendicular, then you have the slope of -1/2. The sign changes and you flip the value upside down. So if you have a slope of -3/4, then the perpendicular line would be +4/3. All right, let's find the perpendicular and parallel lines to a particular line that we have in general format. And then the perpendicular and parallel line has to go through a particular point. I don't know if I said enough P words there. So let's take in general format ax plus by plus c equals 0. Then given a point, we're going to find one line, we'll call it L1, that is parallel to our original line L. And then a second line, L2, that is perpendicular to our line L. Here's an example. Given the general form of 2x minus 3y plus 6 equals 0, we want to find a parallel and a perpendicular line, two lines, that goes through the point 2, 8. Well, what I think is if I can get this line, this 2x minus 3y plus 6 equals 0, if I can get that into slope-intercept form, I will be given the slope. So I got to manipulate this to solve for y. Okay. Once we do that, we find the slope of our original line is 2/3. Now I know something. If another line is parallel, it will share the same slope. Secondly, if another line is perpendicular to this particular line, then it will have the opposite reciprocal to my slope. All right, here we go. So we know the slope of the parallel line is 2/3. We don't know anything else yet. We just know that its slope is 2/3. We also know the perpendicular line, L2, is going to be the opposite reciprocal, so -3/2. We know the slope of L1, we know the slope of L2. Let's use that along with the point of 2, 8 to find the actual equations of L1 and L2. Okay. Now it does say eventually I have to write this in general form. So throwing in my point of y minus y1 equals m times x minus x1, I'm going to get y minus 8 equals 2/3 times x minus 2 will be the parallel line going through point 2, 8. Manipulate that mathematically, you will get the general form of 2x minus 3y plus 20 equals 0. Finding the perpendicular line, we're going to use the opposite reciprocal, same point, but opposite reciprocal for our slope. And do that mathematically, we get 3x plus 2y minus 22 equals 0. Now, what we do in statistics primarily is we'll take a whole bunch of data and we'll find a line that goes through that data the best possible way it can go through the data, being a line. Okay. This line is called a regression line or best squares line because of the math that we do. For now, you're not going to actually do the calculations to figure out the line. You'll be given the line and you'll be given a value and you'll be able to predict the outcome using this linear regression line and a particular point. So let's see that. So here you're given some data. And by plotting these points of the year of 2006, 2007, all the way through 2012, and the data points of registered motorcycles as 6.7, 7.1, and so forth through 9.6, when you plot those on the coordinate plane, it looks something like this. It's not a perfect line. It's not a straight line. See, this little guy, if I tried to draw a line, and I'm going to horribly try and draw a line, try and draw a straight line, just connecting that dot, I'm horrible. If I tried to connect these dots one by one, you'll see that it's not a line. It's a kind of a line, but I have this weird little humpy thing there. So we could use some math calculations to find the line that best fits all these points at the same time. That is linear regression. Now, even though our data doesn't fit perfectly to this line, here's how I can use this line now. I can take this equation of this line to predict the number of registered motorcycle users will be in 2015. Where our X value is the number of years after 2006. So it's not the value of 2015. It's the number of years that it takes from 2006 to get to 2015, which is 9 years. So our X value is going to be 9. Once we plug in 9 into our equation, we're going to get a prediction that 10.66 million registered motorcycles in the US. Now, of course, on this table of data, we don't have 2015. It is a prediction. With the way things are going in the current data, by the time we get to 2015, there'll be 10.66 million registered motorcycle riders. Now, we covered a lot in this video. We covered different forms of lines, whether it was point slope, slope-intercept, the general form. We looked at horizontal and vertical lines. We looked at perpendicular and parallel lines. And then we also used a linear regression line, a line that best fits data, to predict a value in the future by past data. So that's all I want to say for this lesson. Until next time, be seeing you.